Okay, so we're in Hawaii. Astronomy is very important to the Hawaiian culture because they navigate by the stars. They use other things besides the stars, but the wind and the waves and the birds, how they fly, but of course the stars are paramount. I was lucky enough a few years ago to be invited to go to Kololave, which is this island that's off the coast of Maui. During World War II, it was used as a bombing range, so nobody lives there. And so since World War II, they've been cleaning up all the unexploded ordnance that's on the island, and now they're turning it into a research center. So I was invited to go out there to try and come up with some great ideas on how to do research there. But one of the things they showed us was and I'm not good at pronouncing Hawaiian words, but the Kalaki Kahahiki is this site, and this Hawaiian word means the path to Tahiti. So when the Polynesians found Hawaii, they had to figure out how to get back. And so they would train their navigators in this circle. And so you would go to this circle and study the stars. Tahiti is straight that way, right? I had a pointer, but I can point here. So Tahiti is straight out that way. So different times of the year, you would sit in this circle and see where the stars are, so you would memorize the stars and the configuration of the stars so that you know how to guide your ship back home. So this is really the origins of astronomy here in Hawaii. And what were they doing? They were making maps. We've seen tons of maps, right? All these geological maps the past few days. So the first thing you do when you do some sort of science is you draw it up, or you make a map. And so that's what astronomers do. They make maps, okay? But another thing that we do with astronomy is what we call astrophysics. And with astrophysics, we want to be able to predict something, make a model of it, and from that model, predict what's going to happen in the future. So supposedly, the first person that did this, okay, Britt, we'll start moving now. Thales was one of the original Greek philosophers, very smart guy. He was a founder of Western philosophy. He figured out one year that they were going to have a bumper crop of olives, and so he cornered the market on olive presses and got really rich. And he reportedly, now there's a lot of controversy on this, but he reportedly predicted the eclipse, an eclipse that occurred on May 28th, 585 BC, and there was a war going on at the time. Medinians and the Liginians were fighting a war. It had been going on for a number of years, and Thales said, hey, you guys are going to have a battle, and in the middle of that battle, the sun's going to disappear. It did, and they stopped the war. Called a truce, right? Now, whether that's actually accurate, we don't know, but there was enough data for Thales to actually figure that out. Okay, so the Greeks came up with what they thought the universe looked like. So of course the Earth is in the center because we don't move, we're stationary, right? Everything's going around us. The moon and Venus and the sun and Mars, but the stars are fixed, right? The stars don't move, so the stars are fixed, everything else rotates. Okay, yeah. Okay, so it says Plato up at the top. So Plato had this notion that that ideas are true reality. That's the true reality comes from ideas, and that the heavenly bodies, all right, where to go? Heavenly bodies are perfect spheres, and they move in circular, uniform motion. So that's what the heavens are. So this is Plato's idea of how the universe works. But there's a problem. These damn planets wander around, right? So they don't quite fit Plato's idea of how the Earth, how the universe works. So they came up with a solution, and the solution is there's these orbits that the planets go back and forth on. So some of the orbits go clockwise, some of them go counterclockwise, and the planets can jump back and forth between these orbits. So this way they can go one way one night, and the next night they can go the other way, right? Back and forth. And so it was actually Aristotle who started building physical models of this system where these planets can jump back and forth. This is a picture that I took. This was not built by Aristotle. It was built by someone after Aristotle. But this is how complex they had to make it. They had to develop this idea in order to make this system work, right? I think there's 57 nested spheres in this model. I took this at a museum in Florence, Italy, to show this was their concept. So, okay, Brett, next. Okay, so we go along, a few hundred years later, this guy, Ptolemy, a very famous scientist and astrophysicist, I guess we'll call him. This is right around the time of Christ. These ideas of epicycles came about, and Ptolemy came up with a complete cosmology. He described everything with epicycles. What are epicycles? So here's the Earth, planet's going around in this orbit, but the planet is on, you know those Ferris wheels that have cages on them, and the cages spin as the Ferris wheel's going around?
Those are fun.
Yeah, make you sick, right? So that's the idea of epicycle, right? So the planets can be orbiting around, but they can also go around the other way, and that's how they can go. That's the explanation of this forward and backwards motion. So Ptolemy figured it out, right? Okay, go ahead. Yeah, well, I didn't get it quite right. We have to fast forward now. This is like 1,300 years later, right? Over a century, almost a century and a half, until Copernicus came up with this idea that, no, the sun's at the center of the system, and the moon, and only the moon goes around the Earth, and the Earth spins on its axis, and everything else orbits the sun, right? So Copernicus was the one who came up with this idea. No, go ahead. There was a guy, Al-Tusi, in the Islamic world, in a few hundred years before Copernicus. He was known as the father of trigonometry. He also had this idea that maybe the sun was the center of the universe. And he drew up, these are notes from Al-Tusi of how the solar system works, okay? These are the notes of Copernicus. I think Copernicus copied his homework, right? Look at that. Look, this was labeled by Tusi as Dal. Copernicus labeled it D. Alpha, A, right? Jim, G. So it's pretty strong evidence that Copernicus had some inspiration from the Islamic world to come up with his idea that the sun was the center of the universe. Go ahead, Brett. The Islamic world had made great advances during this time. You know, I jumped from Ptolemy all the way to Copernicus, and there was a century and a half. That's because the Western world, Europe, was in the Dark Ages and really wasn't doing much, but the Islamic world was doing a lot. And they actually funded science. The government funded science, and they built all types of new instruments. Go ahead, Rick. With the new instruments, they made measurements. One of the things they did was they measured the height of the atmosphere, right? So the sun goes down, but it doesn't get dark. Why not? Well, because the light, they had a concept of how light works, and the light was scattering off the atmosphere. And so it takes a while for the sun to get far enough away that it won't scatter on the atmosphere above you. So they could, using trigonometry, they calculated that the height of the atmosphere was 52 miles. It's actually 62, not too bad, right? They calculated the circumference of the Earth with the astronomical measurements. They did pretty good. Actually, the Greeks did better than they did, but they're only off 500 miles. But this is the one. Using algebra and astronomy, the Islamic world calculated the length of the year. And this is what our length that we have today. For those of you who can't see it, the Islamic calculation is good to 1, 2, 3, 4, 5 significant figures, right? The difference between the Islamic calculation of the length of the year long before the time of Christ is off. I calculated this a little bit ago. It's off by 0.8 of a second. Not bad, huh? They did pretty good. Okay, next. They had a lot of cosmology in the Islamic world. Al-Kindi had this notion of time. Time could not have existed before the universe was created. Therefore, time must have started at the creation of the universe, right? So a starting of time, that's a whole new concept for humans, right? Al-Burundi, astronomical data could be explained by a sun-centered. So It's even goes further back. And then Bib al-Hatham came up and looked at Ptolemy's cosmology and said it doesn't work. Right? Epicycles are wrong. Right? So there's got to be a different explanation. Go ahead. Okay, so Copernicus comes along, gives his theory out, and people are starting to look at that. Right after that, a guy comes along, Tycho Brahe, very famous astronomer, and the last of the naked eye astronomers. So all the instruments that he built were only naked eye. There was no amplification with optics. His story is kind of interesting. His father, well actually his stepfather, Jorgen Brahe, was a vice admiral. He and his wife couldn't have children, so he convinced his brother that if his brother's wife had twins, that he would get one of the twins. Sure enough, she eventually had twins, and he went to get the son. Caused a little bit of problem within the family, but he won. I mean, if you're a vice admiral, you usually, you can do whatever you want, right? So he inherited the young Tycho Brahe, and then Tycho's father, saved the king of, it's down here, King Frederick of Denmark, fell in off the pier into cold water. The admiral jumps in, saves his life. King's indebted to him. The admiral catches pneumonia and dies. So now the king is like, oh, I gotta, take care of Tycho, the young son. And Tycho gets interested in astronomy because there was an eclipse that went through when he's at a very informative age. It wasn't a full eclipse up in Denmark, but enough for Tycho to get involved. So, go ahead, Rick.
Okay.
So Tycho starts making these naked eye measurements, and he's really lucky, right? Sometimes it's better to be lucky than good, right? A supernova appears in the constellation Cassiopeia at that time, the stars are supposed to be fixed, right? Aristotle in physics says the stars don't change, and all of a sudden the stars are changing, and Tycho is the one there to actually make these measurements. So he becomes very famous very quickly, and go ahead. The king gives him a castle, right? buys him a summer home, and with all of these locations where he can go outside and do astronomy. And so he comes up with, let's go ahead.
Okay.
He comes up with a great experiment. So I'm going to tell you about a bunch of successes in the world of astronomy, but I'm going to tell you about a bunch of failures, because we learn more from our failures than we do from our successes, right? So Tycho knows that when he looks at the Ptolemy's system with the epicycles, that the closest approach of Mars to Earth is 1 astronomical unit. An astronomical unit is the distance between the Earth and the Sun, right? So on closest approach with the epicycle, Mars is 1 astronomical unit away from the Earth. If you look at the Copernicus system, it's only half an astronomical unit, right? So all I have to do is make this measurement. That's a pretty easy measurement to make, I hope, right? Because I got to see if it's 1 or half. Right? There's a big difference. I don't have to measure a tiny little bit. But this is not an easy measurement to make. Go ahead, Rick. So he comes up with his method. This is the distance that he thought was between the sun and the Earth. And then he's going to make a measurement just at dusk as to where Mars is. Then, okay, Brett, again. Then he's going to make a measurement right at dawn where Mars is. And then based on that, he can come up with the geometry of, this is the diameter of the Earth, right? The nighttime measurement to the early daytime measurement. He knows these angles because he's measured them. And if you know this angle and this length, you can calculate anything. Whoa, you're going too fast for me.
Too far.
So, is it 1 AU or a half AU? So in 1582, Mars is in the right location. He makes the measurement, and it doesn't work too good. He gets bad results. He tries again. Oh, no. Before he tries again, go ahead. He builds a better instrument, right? So Tycho is great at that. And these are naked eye instruments. He's down here observing. He has to look out And you know, this is a huge instrument that can give very accurate measurements of the location of Mars. Go ahead. So 1582 tries again in, go ahead, Rick. 1585, guess what? Nope, that didn't work. So now he says, you know what, I'm having a problem with the atmosphere, right? The atmospheric dispersion, because if I'm doing these measurements late in the day or early in the morning, I'm not looking straight up, I'm looking to the horizon, and there's too much atmosphere going through the horizon. So he corrects for atmospheric refraction, does the measurement again in 1587, he nails it, right? He finally gets the answer that he's looking for, but it doesn't really agree with either the one or the half answer, right? So he comes to the conclusion that both Copernicus and Ptolemy were wrong. So I'm going to come up with an even better solution. There was a problem. The distance between the Earth and the Sun at the time, and this is just not Tycho Brahe. This was everybody. They thought it was 7.5 times 10 to the 6th. It was actually, go ahead, Britt. They were off by a factor of 20. 1.5 times 10 to the 8th, right? So way off. So you know, if this is way off, then your result, your experimental result ain't any good, right? So go ahead. Nonetheless, he still thinks he's right. So he comes up with his own solar system. Here's Copernicus. Here's Tycho Brahe. In this system, here's the Earth. The moon goes around the Earth. The sun goes around the Earth. But all the other planets go around the sun. Okay, so there's this kind of multiple merry-go-round, right? Now, this kind of explained a lot, except there's one slight problem here that probably all of you noticed. The sun crosses the path of Mars. Sooner or later, Mars is not going to be very happy, right? When the sun gets in its way. So, works for Tycho, but it's not a real good model. So go ahead, Brett. King Frederick finally dies, and the new king is not enamored with Tycho. He actually he got his nose cut off in a duel. He got in an argument at a wedding over an equation, and he and a mathematician ended up having a duel, and he got his nose cut off. So he wore a prosthetic nose his entire life. But I tell that story just to give you kind of like his personality, right? Yeah. So he didn't get along with the new king, and so he left Denmark and moved to Prague to continue his studies. And he has this problem with Mars, right? Mars is not in the right place. This is what his prediction of where Mars should be, right here, along this river. This is deviation, and this is the actual location of Mars. And every once in a while, it's way, way off. Okay, and that's predictable. That comes about on a very constant cycle, right? So it's something's going on here, right? So he's really having problems with this orbit of Mars. Go ahead, Britt. Just a little bit of background before we take the next step here. Just so you the timeline: Copernicus, Tycho Brahe was right after Copernicus. Kepler was a little bit younger than Brahe. Galileo and Kepler are about the same age, and then Newton comes along a little bit after that. Oh, by the way, there was this little thing with the Council of Trent and Martin Luther and the Protestant Reformation and the Counter-Reformation of the church, and all of these people were fighting, and all of these people get tied up in all of these skirmishes. Just like today, politics really affects the science that goes on. So go ahead. So along comes Kepler. At a young age, he sees some comets and some eclipse of the moon. He gets excited about astronomy. Go ahead, Brett. And he's very smart. He becomes a teacher of astronomy and math at a young age. He develops a successful calendar. He's looking for a hidden cause for the way things work, right? Big question in his mind: why 5 planets and the Earth? So 5 planets and the Earth, there's 6 of them, right? And how about the distance between the planets? Why are they in the distance that they are? Go ahead, Britt. So these are the 2 big questions, right? And he comes. No, go ahead.
Okay.
He comes up with the solution, and it's Platonic solids. Okay, platonic solids, and if you're interested in these platonic solids, just Google it and watch a video of platonic solids. These are amazing things. That if you take a finite length and put it together to make a solid, the simplest solid you can make is a pyramid, and then a cube, and then a hexagon. Then come all these weird things after that. But there's only 5 platonic solids. There's only 5 forms that you can make. And then the next one after that is a sphere, right? So 5 platonic solids make 6 orbits. So Kepler's like, wow, I think I got something here, right? So back up. You went too fast. Okay, so here's the first. I'm going to do this in 2 dimensions because I'm not very good at drawing in 3 dimensions. Okay, so first platonic solid, we draw an orbit. And that's that first orbit inside the platonic solid, right? We can draw another orbit on the outside of the platonic solid. Okay, and then we can inscribe the next platonic solid, the cube, around the circle. Then we can put another orbit around that, right? So I can't go any further in 2 dimensions, but go ahead, Britt, back it out. Keep going. Okay, so with 2 platonic solids, I made 3 orbits, and go ahead, keep going. Keep going. And another one. And the ratio of those orbits, particularly for the inner planets, agrees pretty well with the orbits of the planets. Right? So Kepler, he solved the problem. Huh, he thought. Not so close. So Kepler gets in trouble because of this damn Protestant Reformation in the Inquisition and all that stuff. So he has to change locations, and he goes and finds Tycho and becomes his assistant. Tycho assigns him this orbit of Mars, right? Mars is not in the right place periodically, and Kepler says, I got this, it's the platonic solids things, right? And he tells Tycho, I can solve this in 8 days. I'll come back in 8 days with the solution. Well, no, too fast.
Right, sorry.
So,
It's my fault.
kept taking him a little bit longer than 8 days. Turns out Tycho was enamored and drinking beer, enamored so much that he wouldn't leave the table when he had to relieve himself. And so he held it, and he developed a kidney disease, and it killed him. Right? So shortly after Kepler showed up, Tycho Brahe dies of this kidney disease, and a short 8 years later, he comes up with a solution. Go ahead. And it is elliptical orbits. Right? We found it. Now, this is not a scientific proof. He's just matched the data to the geometry, right? So this is not, this is just empirical data that he's used to find this out. But he's right? So, he was wrong the first time. Second time, looks like he got it right. Okay, go ahead. Again, I'm back over here. So we've just finished Kepler, and now Galileo comes along, right? So Galileo, really interesting guy. He was born in Florence. His father was a musician. His father was in playing music in Pisa, and his father was also an instrument builder, right? And so his father had young Galileo come and stay with him in Pisa, and his father taught him how to build instruments. It's a very important role. And so Galileo grew up in Pisa. Next one. I've been in Pisa. Everyone takes this picture, right? You got to take this picture. This is the Leaning Tower. Sure enough, Galileo dropped balls off the Leaning Tower, and you don't want it to fall down, so you got to hold it up. So shortly after that trip, I was in Florence and visited this museum of science in Florence. Go ahead, Brett. And in there, it has the instruments that Galileo built with his own hands. Okay, so this is an inclined plane that he used to determine the speed of the ball that fell down the inclined plane, and compared it to the speed of the ball that fell directly down, and found that they were the same. Right. So he's studying motion. Go ahead, next one, Brett. Now here's the one that's really great. Next slide. He builds this instrument to look. Go ahead. To look at the trajectory of a projectile. So the way this thing works is you drop the ball, accelerates down here, and then it gets launched. And then these rings, you can adjust them up and down. And so you do the experiment and adjust the rings so that the ball passes right through all of the rings. And once you've done that, you've traced out the path of the projectile. So it's a great a great experiment that Galileo did. What a genius. And oh, by the way, this killed Aristotle in physics, right? Aristotle thought that the ball went like that and then dropped down. Another win for good old Galileo, right? Along comes the telescope. Galileo did not invent the telescope, but he used it. The telescope was originally invented as a protection during wartime for ships at sea to see who's coming after them, see if they're friendly or foe, look long distances. But Galileo was the first guy who took this and pointed it up to the sky. And then, overnight, November 30th, 1609, we know exactly when this happened. And it happened again in January, but go ahead, Britt. He measured the moons that are orbiting Jupiter, right? And if you look at them, and then a few hours later you come back and look at them again, they're in different position, right? Go ahead, Britt, next one. So this is his notebook of different times and different days of where the moons of Jupiter are, and he realizes that they're orbiting Jupiter. He looks at the moon. It's not a perfect orb. It's got dots in it. Now, another insight into Galileo's personality. Once he saw this, it was granted to me alone to discover all the new phenomena in the sky and nothing to anyone else. This is the truth which neither malice nor envy can suppress. Right? God picked me to do this. Right? No one else. Okay, so he measures more things that show that the Earth is moving, and go ahead. He comes to the conclusion that the Earth moves, right? Well, next slide, Brett. That's not in conjunction with what the Holy Father, the Pope, interprets the Scripture according to the Council of Trent, that no interpretation of the Scripture differing from that of the sanctioned by the Holy Father was to be tolerated. So yeah, we can't have Galileo going around saying this stuff. And Galileo says, no, I got this figured out. Go ahead. I can prove to you. So he goes off to Rome to see the Pope. By the way, the Pope was a boyhood friend of his, so he figures he's got it in with the Pope, right? So he goes off to Rome and he says, I can prove to you that the Earth moves, and it's because we have tides, right? So Galileo's explanation is, this is the orbit around the sun, and then this is the Earth orbiting around its axis on a 24-hour period. This is the annual rotation. So at midnight, the Earth's surface is going with the direction of the orbit. But at noon, it's going the other way, right? So the water on the Earth has to slosh around. It's pushing one way and then it's pushing the other way. That's what causes the tides. Go ahead, Rick. I did an experiment to show that it happens. Let it hit it down here. Of course Galileo had figured this out. It's going.
Yeah.
Look at that. The Earth goes, then it stops, goes the other way, the ocean runs to the other side, right? I did this in my office because Barbara wouldn't let me do it in the house. So this was Galileo's explanation. Of course, we all know this is wrong, right? That the tides don't go on a 12-hour cycle, right? So Galileo didn't convince anybody that this was the explanation. So guy does really good work, but he came up with a bad experiment, right? So again, we learn from our mistakes. He gets called before the Inquisition, is forced to bow before the Inquisition, saying that he's wrong. He's given a life sentence, and his daughter, who was a nun, actually wrote up most of his work for him and actually did a lot of more interpretation. So this is probably the first, I'm sure there was some before this, but this is one of the many times that women didn't get their due in science. It was actually Galileo's daughter who did a lot of the work that he did and brought it to publication, if you will. So Galileo is sentenced to house arrest for the rest of his life. Go ahead, Britt.
Trying to.
He finally passes away. and he's buried in a church, but his body is, they break into his grave, and they steal, the only thing they steal from Galileo is this finger, his middle finger, right? The reason for that was, back up a slide. Supposedly, the urban legend is, when he was had to bow before the Inquisition, he murmured, "And yet it moves," the earth moves, and he gave them the one-fingered salute. So, go ahead. So that's why this was stolen, right? You have to preserve the salute that Galileo gave to the Inquisition. It is actually now preserved in this Museum of Science in Florence. It's in this thing here. I'm trying to take a selfie with me in the finger. You can kind of see it there, but who says people don't have humor? So go ahead. The church figures out, gosh, we kind of screwed up with this whole Galileo thing. So they build an observatory in Vatican City, and Rome grows very quickly. They have to move the observatory because of its it's getting too congested. The third time they moved it to Arizona, and this is a telescope that currently exists in Arizona. It's called the Vatican Advanced Technology Telescope. We call it the VAT, and people from New Mexico Tech use it quite often. It's not far from Socorro. You just go out Highway 60, and shortly after you get into Arizona, you're at the VAT, and you can use it. So Jesuit priests run this, and the person who's currently the head Jesuit priest that runs this observatory has a PhD in cosmology. So they're studying cosmology. Go ahead, next. Okay, now comes along Newton, next. Newton has to go home because there's a plague. This is kind of like COVID at the time, right? So everyone's sent home for 2 years. So at the tender age of 23 and 25, he comes up with this idea that the Earth's attraction to the moon and the Earth's attraction to an apple falling from the tree are the same. It probably is a true story that he was watching this apple fall from the tree. That's the tree that they historically say is the one that he was watching the apple fall from. And so he compares the force of gravity on Earth to the moon being captured in its orbit. Go ahead, Fred. Oh yeah, while he's in Bolthorpe for a couple of years, he does a few things like infinite series, differential calculus, theory of colors, integral calculus, inverse square law of dependence, fourths of distance. This is what you'd normally do on a stay-at-home, right? Okay, so he comes. The plague is over. He goes back. Everybody realizes, man, this guy really knows what he's doing. He's elected to the Royal Society at the tender age of 30. And he gets into a big argument with Robert Hooke. Yes, Hooke's law, right? Spring constant. Galileo said that light came in corpuscles, and Hooke said, no, it has to come in waves. Of course, we all know that light has dual, right? So they were both right, but at the time they didn't know that. So big, and this turns into a mess, right? A really messy fight. And eventually, Newton says, if I have seen further than you, it is by standing on the shoulders of giants, right? So everyone assumes that what Galileo means is I'm using Copernicus and Galileo and Kepler to make my predictions. And I'm standing on the shoulders of those giants, and so I'm right. That's not what he meant, right? The people who really studied this. Turns out Hooke was a dwarf, and Galileo was making fun of his stature, right? He says, I stand on the shoulders of giants. You're way down there. You can't see anything, right? I'm the smart one. But Newton is a very social, not really socially good at interacting socially. He would fit right in at New Mexico Tech. So he goes back to Cambridge. Right? To study alchemy and theological exploration, right? So he's studying away. Go ahead, next one. And Edmund Halley and Halley, Hooke, and Wern, they figure on their own that there's this inverse square law of this force at a distance because of orbits. But if you have an inverse square law, then what kind of orbit would that produce? That's the question. They don't know the answer to it. And Halley says, I'm going to go ask Newton. I'm going to go find Newton and ask him. So he searches Newton out, asks him the question, and Newton says, yeah, I already solved that. But I got to go find my notes, right? So, go ahead. a short 2 years later, and apparently Newton had solved it, but he went over his calculations again and again and again because he didn't want to get in another fight, right? He really wanted to avoid this fight that he got at the Royal Society. So he takes 2 years, publishes the Principality, and that gives all the explanation you need for the inverse square law, gives you elliptical orbits. And now we have a model of how this thing works. Go ahead, Rick. This is a very interesting thing about Newton, is that if the universe is finite, it will collapse due to gravity, right? So if I have all these things in the universe, they're all going to attract each other, right? So first of all, since we know the universe is static, the stars have not changed over the eons. If it's infinite, then we can balance gravity out so that the stars are fixed, right? And for Newton, this was a proof that God exists. Okay, so God arranged the stars so that there's one star right here, and there's another star over here pulling it this way. But then there's another star in the exact right position pulling it this way so that it doesn't move, right? And if you have an infinite number of these spread out over the universe, then everything's in good shape, right? So Newton goes, this is why, there's a quote down here from Newton, this is why we know there's a God, is because the universe is static. Go ahead. Okay, so Newton invents a new telescope and then let the discoveries begin. Go ahead and go through these. Oh yeah, this is a brother and sister team, William and Carol Herschel. They build a really big telescope and they start discovering a whole bunch of stuff again. Actually, Carolyn did get a little bit of credit for this. Her brother got a lot more credit, but yeah, another time when science shuns female scientists. Of course, so all the outer planets get discovered. Go ahead, next. The asteroids get discovered with these big new telescopes again. Nebula are discovered. I'm not quite sure what they are when they're discovered. Go ahead. But then spectroscopy comes along, right? So we're looking at these things through telescopes, but now we can look at their spectrum, and we can tell things about atoms and molecules that exist on these stars. Go ahead, Rick. And because of that, we can classify stars, right? So around the beginning of the 1900s, spectroscopy really comes on, and we can start classifying these things that we see in the sky. Go ahead next. Oh, Einstein comes along. I know I had to put in a differential equation, so here it is. Okay, Einstein comes along, he writes down the general theory of relativity, and the general theory of relativity that he wrote down at first predicts that the universe is dynamic. The universe should be contracting upon itself because of gravity, right? Well, Einstein knows it's not, right? The universe is static. So he introduces what's called the cosmological constant. Go ahead, Rick. That cosmological constant, hit it again. It represents the energy density of the vacuum in space, right? So Einstein adds the cosmological constant to his differential equations to freeze the universe. Well, we know we can add a constant to a differential equation, right? It doesn't change it. All it does is it changes its starting location, right? Of the solution to the differential equation. So what Einstein is doing by introducing the cosmological constant is putting all the stars in the right location so that they balance out, right? It's not that Einstein believes in God. He just says, this is how it works. Okay, so everything's right? But there's a couple of questions. How big is the universe? Why isn't the universe heating up? We have all these stars that are burning. They give off heat. So shouldn't the universe be heating up? Go ahead, Brent. So in order to solve some of these questions, along comes Henrietta Swan Leavitt. This is probably the biggest person in astronomy who got snubbed because a bunch of her bosses took credit for the work that she did. She was what was called a computer at Harvard College Observatory, and she came up with this relationship. There's these special stars called Cepheids that they pulse, and they pulse. They get brighter and dimmer over the course of a few days. Okay, and the period of their pulsation you can determine how much light is being sent out from each star. So the pulsation is essentially a measure of how bright the star is, and now you can compare these different stars and their pulsation rates, and you can order the distances. So these are what we call standard candles, right? So if I had a standard candle far enough away from me and I measured how much light I get, I know how far it is. So this is a way to measure those distances. Yeah, go ahead. So Hubble uses Henrietta Leavitt Swan Cepheids to measure the distance to the Andromeda Nebula. And guess what? It's way out there, right? It's far, far, far away. It's not in our galaxy. The universe just got huge because of what Hubble measured. Hubble measure, and this is, and then Hubble also measures the redshift of these things. And what Hubble finds, go ahead, Rick, is that the redshift gets bigger as you go further away, which means the universe is expanding. Einstein had literally said, the biggest mistake I ever made was adding the cosmological constant, right? He didn't need it. The universe is dynamic, right? So before Hubble even discovered this, though, this guy, George Lemaître, a priest, came up with this idea that maybe the universe started as a singularity. He was a mathematician. And it's expanding. And then Hubble makes that measurement, and sure enough, it is expanding. Go ahead, Rick. So now there's other questions that are coming up. Does the Earth expand forever? Does it come back on itself? Go ahead, next. We need to determine the density of the universe to see if it expands or contracts, right? Go. Gamow says, okay, given the density, we should be able to know what the background temperature is. He predicts a background temperature of around 5 degrees Kelvin. And then in the late 1960s, early 1970s, they won the Nobel Prize in '78. Wilson and Penzias are trying to do microwave communications across the Atlantic. And so they want to get a really quiet system, so they're trying to reduce the background in their horn, and they can't get the background to go away. They always get this background, and they discover that it's 2.75 degrees, and that is actually the background temperature of the cosmic microwave background, right? So they measured it by accident. This is what Gamow was predicting. Okay, go. So now we have the Big Bang. So what happens? In the first microseconds, the Big Bang inflates. There's also all this energy. This energy starts in a microsecond, starts producing protons, and then we start to have fission take place. So helium or hydrogen turns into helium, and then about 3 minutes, that process stops, and then from 3 minutes to 380,000 years, everything is so dense that the light can't escape. So everything, the universe is slowly expanding, but too much density for light to travel freely. At 380,000 years, light finally escapes, and this is where we have the cosmic microwave background, and then there's nothing going on for a few billion years. This 3.8 is the age of the whole universe, but nothing's happening until these molecules collect together and start to form stars and then galaxies. Go ahead. And these stars have different paths they can produce. One is a supernova, and that's how you get heavier elements. Go ahead. So we're still trying to answer this question: is the universe closed? Does it just kind of go on forever, or does it just coast bigger and bigger and bigger? Go ahead, Rick. So people start making measurements. Fritz Zwicky made a measurement in 1933 of the Coma cluster. This is a group of galaxies that are rotating around themselves. They're rotating too fast in order for the gravity to hold them together. So there's not enough gravity to hold the Coma cluster together. Gravity meaning how much gravity there is from the visible light that we see. Go ahead, next. Here's someone who actually did get some, here's a female who actually did get some good credit, Vera Rubin. In 1975, she made some measurements, go ahead, Britt, of how galaxies, the outer spiral arms rotate. If you depend on just the gravity that we see inside the galaxy, this is what we would expect. What we observe is that there's a lot faster rotation out here, which means there's more mass out here, right? But we can't see that mass. So what do? Oh, I'm sorry. Here's all, no, go ahead. Here's all the things that say there's not enough mass in the universe. There's not enough mass in the Milky Way to do that. Stellar velocities are too high. The Coma clusters should fly apart. Rotation rates, and there's gravitational lensing. And so what do? We invent dark matter. Okay? And we believe that dark matter composes about 85% of the total mass of the universe. Right? So we know everything there is about particle physics. Well, we only know about 15% of the particles, right? The other 85% we don't know. So this dark matter only interacts with gravitational and weak force. And so we call them weakly interactive massive particles, or WIMPs. Right? There's also machos. They're another type of particle. Go ahead. So, more problems. Go ahead, Rick. The universe is actually accelerating. So now we have to come up with another thing. We invent dark energy, right? No, too fast. We have to invent dark energy, right? And so this dark energy is what's pushing the universe apart. We hope. That's what we're trying to work on these days. Next. So what are we doing now? Okay, the JWST, this is the new telescope, space telescope that was launched. It's taken the place of Hubble. They have found, this is like in the first few weeks, they found these galaxies. They looked way, way back in time. So if you look at things that are very, very far away, you're looking at something that happened a long, long, long time ago. So these are the first galaxies that ever formed during the Big Bang. And it turns out that these galaxies are way too complex, way too much mass in them for them to form in the period that we think they formed. So they're being called universe busters, right? The discoveries that the James Webb is making, we got to figure out what these things are. Just too big a galaxy, too complex of a galaxy, too early in the life of the universe. Another thing that we do, I'm going to give you a pitch right now on telescopes. I got to use another equation, right? The resolution of the equation is the wavelength that you measure divided by the diameter. If you look at that, Galileo's telescope resolution, so the smaller r, the better. Galileo's resolution was about 10 to the minus fifth. The VLA, it's only a little bit better than Galileo's telescope. But the VLA looks at very big things, right? They use big wavelengths, 10 centimeters, but they look at very big things. The TMT 30-meter telescope, which is the new telescope that they hope to build here in Hawaii, it's going to be about 2 orders of magnitude better than the VLA, and then the Magdalena Ridge Observatory, the interferometer, we're even better than the TMT. Go ahead, Rick. So this is the telescope that we're building at New Mexico Tech. It's a series of multiple telescopes where we combine the light from each telescope to get this super huge resolution. When we're fully operational, our diameter of our lens is over 400 meters, and so we have a huge telescope. Currently, we have one telescope. The second telescope is actually being assembled right now and will go into the array, and the third telescope is starting to be built. And hopefully, in about 10 years, we'll have all 10 telescopes. Tomorrow, we're going to the Canadian-France-Hawaii telescope. It's the reason you want to build observatories here in Hawaii is because it's up above the marine layer. Yesterday, some of you heard me say, look, out there towards Maui, there's a bunch of clouds, but above the clouds there was nothing. So that's really good. All the moisture is down. Here in Hawaii, we get up above the moisture at very high altitude. So the less atmosphere above us, the better for viewing astronomical objects from the ground. So we're going to look at Canadian-France-Hawaii telescope. We're going to look at Keck. Keck is 2 telescopes that can work independently or together, and they use something called guide stars. So they shoot a laser up into the upper atmosphere, and there's a sodium layer at the top of the atmosphere. The lasers activate that sodium, and that gives off a glow, and we know exactly what that glow should look like. So when we see the glow, so this activates the glow, and then the signal comes back down into the telescope, and then we can adjust the mirror, adaptive optics. We can adjust the mirror so that we get the right wavefront. So we correct for the atmosphere with this stuff. When this was built, it was the largest telescope in the world, 10 meters. Now the largest telescope in the world is the LBT, the Large Binocular Telescope in Arizona, and then there's also one in the Canary Islands. They're just a little bit over 11 meters, a little bit over 10 meters, and this one is the 3rd largest telescope in the world. Go ahead, Brett. What they hope to build here in Hawaii is the 30-meter telescope. It's a bunch of segmented mirrors that go together. Very, very controversial. Construction has been stopped because the native Hawaiians say that it's going to take away their sacred ground. And I've been doing a random survey while I've been here in Hawaii, asking people, what do you think about the TMT? Right? People are either for it or against it, it seems like. And I have a couple of friends who are very involved in this. So one of them is a big supporter of the TMT, Jackie Hoover. She actually arranged the trip that we're taking tomorrow. And Jackie really, really supports this. And if you ask her, we are going to build this thing no matter what. Right? She's a native Hawaiian. My good friend at the University of Hawaii, Carl Kim, who been an administrator for a long time at University of Hawaii. He's like, and the University of Hawaii is leading this program. It's like we screwed this up. We screwed it up from the beginning. We pissed off the native Hawaiians. We're never going to build this, right? So some of my friends think it's going to be built. Some of my friends think it's never going to be built. And I'll quote Bruce King, former governor of New Mexico. Some of my friends are for it. Some of my friends are against it. And I support my friends. I think that's it. Right? Yep. So, questions? We get 3 minutes to spare.
Impressive. It's because you had a really good.
Oh, I had a good.
Another teaser.
Put everybody to sleep.
Questions?
Have you seen the recent, well, I think it was in Apple News this week about the black holes that they found that were loose and are traveling?
Black holes are like another area that I didn't go through the scientific missions because I was just too short on time on these different telescopes. But black holes, we now are convinced that every galaxy has a black hole at its center. Okay, and one of the big things we're looking for is gravity waves, right? So when galaxies collide with other galaxies and the black holes run into each other, they should give off these big gravity waves, and so we're looking to find those. But yeah, but there may be black holes that are not associated with galaxies that can wander around and run into stuff.
They found one that is like trying to escape its galaxy. So.
Or the galaxy's trying to escape it.
It might be a mutual thing.
There's lots of interesting theories about black holes as to what happens to the stuff that falls into the black holes, and is this going to a different dimension, and string theory and all that other stuff. But that's way out there.
Super black hole with the singular galaxy.
Yeah.
So how does LIGO, the laser interference gravitational observatory, fit into all of this?
Right. So LIGO is a L.
Right.
Right. They have two lasers that go down this long path length and then come back to the center, and they match the path length exactly down to a wavelength. Right. So this long line is matched to within a few nanometers. Okay, so it just sits there and waits, and as gravity comes along, we know from Einstein that gravity warps space, right? It warps space and time, and so as a gravity wave comes along, it will affect these two lengths differently, and so the path length will change a tiny bit, and they'll be able to detect that. So there's an experiment. There's a funding at the University of Minnesota to look at the optical analog. So LIGO finds something. Oh, there's a gravity wave from over there, and then this experiment at University of Minnesota is going to direct its telescopes to look at it really quick. Well, they want to locate it. So they want to put a telescope on both sides of the Earth. So one of them is going in Greece, and the other one they're testing the Magdalena Ridge at New Mexico Tech to place the other one. And so they'll get a triangulation on that. These are small telescopes, but they can move very, very fast. So as soon as LIGO sees something, boom, they'll go take a look at it.
So is there a delay in what you should see in the telescope from the gravitational wave? Or
We don't.
what is that delay?
We have no clue.
Okay.
What's what we want to find out?
That's okay.
Okay. If we knew the answer, we wouldn't have to do the experiment.
No, you know the answer. You gotta prove it with the experiment.
Well, yeah, I mean that's what Plato used to do, right? Yeah, I know the answer. Just give me the data that proves it.
Yeah.
Right.
Yeah.
Maybe a statistician.
Yeah. Yes, as was it,
I can't think of it.
Mark Twain said.
Yeah.
There's liars, there's damn liars, and then there's statisticians, right?
So do all these increasingly large telescopes make the old ones obsolete, or do they still?
Oh, that is a great question. And my answer to that, because I've been asked that question many times, right? By the time you build it, it'll be obsolete, right? These things literally take 20 years to build, and TMT is going to take even longer. But my answer to that is Mount Wilson, just outside of Los Angeles, in the telescope that was built there was started construction, I think, in 1904, completed in about 1918, or somewhere along that time. That's the telescope that Hubble used to measure the expansion of the galaxy. At the time it was built, it was the largest telescope in the world. So that telescope is over 100 years old. It's still being used today to do scientific work, right? So we can always find something good to do with telescopes. Maybe making better maps, doing surveys, or it may be totally focusing on one thing and measuring it day after day after day. Right? Oh, by the way, with our interferometer, we have enough resolution to start being able to measure the movement of those stars, right? The reason we can't measure, the reason we think stars have been fixed throughout time is because we don't have an instrument that's delicate enough to measure the parallax, the motion. At this point, we will. We'll be able to see things moving over the course of a year time frame. So we've gone from, I like to say that when we measure the redshift of galaxies, that's like being in a car with the windows blacked out, but you can see the speedometer, right? I know how fast it's going, I just don't know where it's going, right? Now we're gonna roll down the windows and be able to look outside and see where we're going with a new telescope. So tomorrow we'll go up and we'll see them.
I have a question about tomorrow.
Question about what?
How much time are we going to spend outside?
Oh, okay. So we're not going to spend much time at all outside. One of the people that's